All right, let's talk about something we've all been through. You ever been haunted by a mystery outage? You know the one, that critical failure that just pops up out of nowhere with no obvious cause? Well, what if I told you those mysteries aren't really mysteries at all? Today, we are going to dive into how to architect systems that don't just run, they're actually built to survive.
And this right here? This is the core idea for this entire explainer. It's about a fundamental shift in how we think. We're moving from being reactive firefighters who are constantly fixing broken things to being proactive architects who stop them from breaking in the first place.
I just love this term, planning debt. It's perfect, right? It's just like technical debt in software. It's the buildup of all those little unchecked assumptions, all the validation steps you skipped, and the prerequisites you didn't quite verify. And believe me, that debt always comes due, and it's usually at the absolute worst possible moment.
And that really is the million-dollar question, isn't it? I mean, look, anyone can click Next, Next, Finish on an installer. But to consciously build a system that can take a punch, that can adapt to change, and it stays stable over its entire life cycle, now that is the real engineering skill we're here to talk about.
Okay, so let's get into the heart of it. This is our central mental model, the huge difference between installable and survivable. And I'm telling you, getting this right will completely change how you approach building and managing your systems.
So on one side, you've got deployment planning. This is all about getting to day one successfully. It's your checklist, your prerequisites, your dependencies, all the stuff that makes the installation repeatable and clean. But on the other, far more important side, you have design considerations. This is about day 2 and day 730 and beyond. These are the big foundational choices that decide how the system will behave, how it will operate, and, this is crucial, how it will fail down the road.
You know, what's really great about this slide is how simple it makes everything. Seriously, if you take away just one single thing today, let it be this. A good plan gets you in the door. A good design lets you live in the house for years without the whole roof caving in. So how do we absolutely guarantee a system is installable? Simple. We use a pre-flight checklist. Just like a pilot, this is how we systematically knock out all the variables to make sure we have a smooth, predictable, and stress-free deployment. And this is where it all clicks. This table shows you exactly why that checklist is so vital. See, each prerequisite is tied to a really specific, totally predictable failure signature. So, for example, if your DNS for reverse lookups is busted, you're going to see services fail to register. It's a guarantee. If your NTP is off, get ready for some bizarre, intermittent authentication errors that make no sense. And my personal favorite, if your MTU, that's your maximum transmission unit, your network packet size, if that's inconsistent, you'll see huge transfers like a vMotion just mysteriously fail, even though a simple ping works just fine. It's the kind of thing that drives your team absolutely nuts. But here's the key. None of this is random. It's predictable.
So the big takeaway here is really simple. You want a boring installation. No drama, no late-night troubleshooting calls. A boring install is the ultimate sign of a professional. It means the real work, the planning, was done right.
Okay, the system is up and running. Great. Now our focus has to shift from planning to design. And here's a little secret. Every single design choice you make is also a choice about how your system is going to fail. You are literally choosing your future failure modes ahead of time. Let's take networking as an example. You could use a vSphere standard switch. It has a smaller blast radius, which is good. A mistake only affects one host. But the trade-off is a high risk of configuration drift over time. A vSphere distributed switch, on the other hand, totally solves that drift problem with central management. But the trade-off is a much, much larger blast radius. One wrong click can take out an entire cluster. See? There's no single best choice here, only the right trade-off for how your team operates. And the exact same logic applies to storage. With something like vSAN, your storage health is super tightly coupled to the cluster and the network. A network problem can easily look like a storage crisis. But with external storage, the dependencies are totally different. Your cluster can be perfectly healthy, but a failure on an external array or a bad fiber path can bring everything grinding to a halt. You're designing your future troubleshooting sessions right now.
So when a problem does pop up, how do you trace it back to a design choice? Well, you can use a pretty simple framework. First thing, identify the scope. Is it just one host acting weirdly? That smells like drift. Or did everything break at once? That's probably a large blast radius event. Next, you isolate the plane. Is it a control plane problem, like tasks are failing? Or is it a data plane issue, like VM traffic is dropping? When you map these symptoms back, they almost always point directly to that original design choice.
And this brings us all the way back around to the ultimate goal of all this meticulous planning and all this thoughtful design. Now, it might sound a little strange, but what we're really, truly striving for is to build a system that is completely and utterly boring.
Yeah, it really all comes down to this. Good planning makes day one completely uneventful, but great design makes the next 2 years uneventful. Predictable, stable, drama-free operations, that, my friends, is the real definition of success in systems engineering.
And so, I'll leave you with this one last thought to chew on. As you look at the systems you manage today or the new ones you're about to build, just ask yourself that one fundamental question. Is this architecture just designed to get installed, or is it truly designed to survive? Thanks for joining this explainer.